see cars everywhere, sorry, I mean, smart cities, plane, and also maritime transportation. So the I mean, the idea behind is together a set of intelligent transportation systems to improve resource utilization, safety and security, to develop also services and of course to preserve our environment and to respect our environment and the nature also. So this is why we develop, I mean, ITS driven by wireless communications technologies. So let us now go through the agenda of this morning. I will start by maybe presenting something about autonomous vehicles, but not deeply in technical contributions. I just give something about what's going on in the standards and also the use cases and how 5G enabling technologies will enable us to do this, or to realize these case uses which have been, I mean, proposed by the different standard organizations in the world. In order to go deeply inside and technically inside vehicular communications, Dr. Andy Trewinarku, who prepared his PhD under my supervision, who is an excellent researcher actually. And now it's really a very good news that he's returned back to Batam. He was in Canada, in Sherbrooke, and the professor who attended his PhD defense, proposed him 1.5 year postdoc in Sherbrooke University, which is the Center of Excellencies in Transportation in Canada. So he will speak about vehicular communications, about technical maybe solutions to enhance coverage range and security in vehicular communications. For me, just after I will go towards, autonomous train-based 5G and beyond enabling technologies. I will explain how we will make use of what is already done in vehicular communications and how we can apply these techniques, these technologies in railway communications. And at the end, I will, of course, present some results, not theoretical results. I will present a real demonstrator for the first autonomous train with 50 kilometers trip around Paris, which was actually one of our results. First of all, here we can, sorry, I'll just leave this because my screen is.
You don't share the full screen. You don't share the full screen of your presentation.
See, I did, no?
Yeah.
Okay, so this. Okay, okay. So I will maybe. Sorry, how to. Yeah, now it's okay. Is it okay now?
No, it's okay.
Okay, thank you.
Thank you.
So the first one here, the first picture is about vehicular communications. And why I cannot see on my screen? Sorry, just 1 second to manage that. this one. Yes, like this. Okay. And my picture here.
You want to put it?
Yes, to put it.
Excuse me.
Yes. Now it's better. Thank you. So the definition of no, not. Yes, as we can see here, I mean, associating wireless communications to smart vehicles to give, I mean, intelligent transportation system. Actually, here in vehicular communications will enable us to, of course, to reach two applications, or two kinds of applications. First of all, safety applications, which does mean, I mean, minimizing accidents, and all the other applications, no safety, actually, like traffic management, which I mean, automatically will allow to solve a lot of problems, including congestion, including, I mean, how to improve productivity, economic productivity, in addition, of course, to provide a lot of I mean, infotainment services such as internet, or all applications related to internets inside vehicles. Here, different types of vehicular communications. The term V2X, I mean, does mean vehicular to everything, all vehicular communications, such as vehicular to pedestrian, or vehicular to infrastructure, or vehicle-to-vehicle communications, or vehicle to networks. The different international organizations in automotive organizations define different automation levels, from level 0 up to level 5, I mean. Where in level 0, no automation, and the driver performs all tasks, while in 5, I mean, level 5 or even 4 in the States, regarding NHTSA, which is American standardization, here the driver, I mean, has nothing to do, and the vehicle is in full automation mode. So the these organizations, standardization organizations, actually they defined a set of use cases, a group of use cases, and each group will, I mean, provide a couple of services. And we will see, of course, immediately that the only way to realize these use cases in full, I mean, security and full efficiency will be wireless communications technologies. We don't have another choice to go through wireless communications technologies. And here we will define some of these use cases already standardized, already defined. I mean, but in Europe, a small difference, maybe Andy will speak about these differences compared to the definitions in the States. Anyway, from the first group of use cases, vehicular platooning, which does mean that vehicles exchange messages and information in order to form, I mean, this platoon. They will elect the platoon leader. They will enable vehicles to join or to leave, and also messages will be exchanged with neighboring in order to warn about vehicles which will join or which will leave, and the possibility to avoid, I mean, the problems with vehicles which are not from the plateau. This is, I mean, the first kind of use case. The second one, changing driving mode. Here we have a platon. This platon is led by vehicle A. In case of an obstacle, of course, vehicle B should have the possibility to change the driving mode and to, I mean, to leave the platon and to be under, self-driving, autonomous driving in order to avoid collusion with this vehicle E. Here, remote driving use case, and the general architecture is very simple. Actually, these vehicles can be driven remoted either by someone who is, I mean, very far from the vehicle, or by some software applications, but not inside. I mean, software applications outside and in the cloud computing level. And of course, this is possible thanks to wireless communications, as we can see, and also high data rates, enabling us to make use of videos and sensors, and this is will help, of course, this use case. Another one, extended sensors, and here we can see easily that this vehicle will extend the sensors possibility of this one through, I mean, some applications, and this vehicle will be aware and will avoid accidents. Vehicle E. Now, here, advanced driving, okay, but I will not, that's very simple to show. I mean, advanced driving based on information sharing between traffic signals, radar, road radar, and also roadside units. All these interfaces and the sharing of information will avoid possible accident, and will, I mean, lead to stop this car before attending the man in front. Now, before, I mean, finishing with this first part, I would like just to show how the set of 5G enabling technologies can be mapped with use cases, and this is our proposal, and we are really proud of this proposal, done and very recently. And as you can see, the statistics, I mean, it's cited a lot, read a lot, and this figure is, we can find it in all, I mean, major publications in the area since 2021. So the idea is, as we know, 5G, we have 3 pillars. I mean, the EMBB, which enhanced mobile broadband, and I mean, ultra reliable low latency communications and massive machine-to-machine communications. We, I mean, classified the use cases, and we can see that all, I mean, data driving use cases which needs high data rates can be, I mean, based on EMBB pillar for 5G, while, I mean, sensitive applications which need end-to-end ultra reliable low latency can, I mean, make use of this definition of 5G, and massive connected objects, as you mentioned, I mean, at the beginning of this webinar. Internet of Things or connected devices. I mean, we have a lot, and we need, of course, this massive communication and all applications related to this huge quantity of devices, huge quantity of shared informations will make use of this pillar of 5G communications. So now I finish with this first part, and Dr. Andy Trawinarko will go, deeply, and will show some technical solutions, and some of these solutions he will, speak about. Has been already considered by North American standards. Now, the idea here is to show you how we are working in Europe, and how we are translating the main ideas in vehicular communications in cars to railway and the trains, because trains are very interesting. They are the economic solution, in Europe, and environment, friendly. So this part will be divided in 3 up to 4 points. First of all, some challenges, wireless communications for railways, and then I will go through 2 or 3 projects, ongoing projects, of course. So the context, by similarity to vehicular communications, the idea here is to improve, to develop the railway sector, and this is will lead to, of course, automated. That does mean we can imagine by automated virtual coupling while we are outside cities, for example, to autonomous driverlessly conducted, and also other use cases which I will present immediately. So, of course, as we know, this will need high data exchange. This will need high capacity of networks, and of course we will go through 5G and the 3 pillars in particular. Low latency, high data rates, and high quality. So we can define 3 categories of vehicles-based train communications, if you want. T to T, train to train, train to ground, and intra-train communications, which does mean all the entertainment applications. So there are the pillars of 5G, and the idea here is to prepare the after GSMR. As we know, GSMR is the obsolete mondial standard now. Unfortunately, it will be finish in a couple of years, maybe 2027, because the lifetime of a train, which is 30 years, and the GSMR has been launched in 96, 97. So we are about the end of this GSMR. So the main players in the area, in the main industrials and also governments in Europe and in the world, actually, they are preparing the day after, from 2016 or 17. And the idea is to go towards the FRM, which is Future Railway Mobile Communication Systems. How to do that? I will not, go through details in organization or standardizations. But briefly, the IUR or International Union for Railways and European Railway Area, they started developing next generation of train control systems around 2010. Then after this huge project, leaded actually the players in Europe to the future railway mobile communication systems. The idea is to go towards what we can maybe what we can imagine today 5G-R, not GSM-R. 5G-R, that does mean 5G railway. So the idea is to cover both critical applications, critical, like the critical ones in vehicular, driveless train, virtual coupling and decoupling of trains, and this is control command applications, and also no critical, all applications related to entertainment and applications such as video, augmented reality, videos, or maybe webinar like we are doing now. We can do that from the train, regardless the vitesse of the train, of course. So in 2016 to 2017, the huge project Shift to Rail has been launched. The main objective is to go to this future future railway mobile communication systems. So the challenges, as you know, we are under different systems, 4G, 3G, 5G. We have a lot of technologies, a lot of solutions, first of all. Then we are in different countries, so different regulations and different policy and different strategies, and also we have some technical challenges related to the environment, in particular the vitesse and also the noise nature, which is not Gaussian at all in this kind of areas. Anyway, so the idea is here, and the project is Shift to Rail, Shift to FRMS in the next future. And by the way, this huge project has defined a couple of innovation programs. The one which interested us is the IP2, and the IP2 Advanced Traffic Management and Control System. The target of this innovation program is to do some demonstrators, to realize demonstrators and to show this demonstration before the standardization step. And the target was December 2022. So we are inside, and I will show you some of these demonstrators at the end of this presentation. Anyway, so through this IP2, what has been decided is the all the wireless communication environment of this global 5G-R. A lot of tasks, and the objective, final objective, is to go through adaptable communications for all railways. Adaptable, what does it mean? We can make use of all 5G and beyond enabling technologies. So we will not be dependent of a specific technology like GSMR. So we will be adaptable, okay? And many radio interfaces, many technologies will help in, communicating, ensuring communication between the services, inside or outside the train, and for automatic train control, automatic train operation, and also for all the operation of signaling and all this critical applications. So now this is the adaptable architecture, and this new concept and adaptable architectures will give a lot of advantages compared to legacy networks, in particular, and in particular, of course, the independency of the technology lifetime. This is the first. The second one is, of course, the to meet the free 5G pillar applications in terms of latency, data rates, and also quality. So here we are about proposals. This is the 5G PPP or 5G R proposal for this 5G system. I still have 5 minutes, or?
Yes, please continue, sir, no problem.
Okay. So this is the this one of our, one of the visions, and we are completely here. The idea here is to go through cognitive radio and dynamic spectrum allocation in order to make use of the underutilized spectrum under the band of 6 gigahertz. And I will not, go through these functions, but the idea is to, we know that the spectrum is completely now used under, of course, 6 giga. So here, how to do dynamic spectrum allocation with this CRRM, including a lot of software-defined radio functions. So now the 5G and beyond enabling technologies, a lot of solutions. In addition to the cognitive radio and spectrum, dynamic spectrum sensing, we have all radio access technology, in particular what is going on now, NOMA or non-orthogonal multiple access, and also the spectrum band above 6, in particular from 10 up to 300 giga, what we call, millimetric wave communications. And we are absolutely inside in order to also make use of massive connectivities or massive MIMO. And by this, I will just introduce the principle of NOMA compared to OMA. OMA, orthogonal for 4G, and that's all. And also for 5G, now the standardization, keeps OFDM and keeps OMA. NOMA, as we can see, no orthogonal, that does mean no need to reserve, any resource for users who are not exerting activities. And the idea is to share the power between users regarding the distance from the base station. So this will, of course, enhance the data rates and the efficiency of the network. Now, regarding the millimetric wave communications, the band above 6 giga, we are with millimetric, waves. So we have a lot of challenges, penetration losses in all materials, including wood, inside we are affected, outside we are also affected. And also the atmospheric absorption. So a lot of bands will be, excluded from the party. And the channel of millimetric wave is completely sparse channel, and this will, of course, complicate the task of channel estimation and the tracking, in particular when we are in vehicular communications. So as we are in millimetric waves, so the antenna size will be very small, and we will, of course, realize massive MIMO. That does mean a lot of antennas and the possibility to control the directions of these antennas in order to subdivide it, a particular zone in sectors. We have also the beamforming and the possibility of tracking and to go to a specific direction, specific user, and this will be done by what we call codebook design from the emitter side. Codebook design will master, of course, the directivity of this of these beams, and we will have a dynamic and of course auto programmed antennas like this one. This is one also of what we have proposed to literature. Lens antenna and the possibility to control through RF circuits, and it's just one of the scenario for this millimetric wave communications. Now, one of the challenges is also the doubly selective in this environment. As we can see, without speed, we can obtain the energy on users directly, but this is dissipated because of the Vites here, and this will affect the interference at more than two levels. The first one between users, and the second one between services also. Another huge problem is the noise. It's not Gaussian at all, it's impulsive because of these contacts. And the impulsive noise should be, treated. I will finish by these two projects. The first one, millimetric wave for rail, launched last year, finished 2024. The objective is to go towards train-to-train and the train-to-infrastructure, ground communication using millimetric waves. The mean is, to maybe to serve three use cases: train-ground communication, train-ground in specific areas, and the train communication for virtual coupling. Of course, taking in consideration all the scenario and the critical scenarios, like this movement, or maybe in tunnels. This one is the autonomous train, TC rail, with always with the major players in Europe. Like here we have Mitsubishi as a key partner. Here we have other key partners also, and this is under development, and we have a lot, as mentioned Mr. Gary, a lot of results, and I will finish just here to show you one of our demonstrators. It is on the national TV. Ne voyez pas.
You share your slide, but you click the YouTube. I think it's not shared here.
What to do?
Maybe you should stop the presentation, and now you share again, but this time with your YouTube.
Okay.
We see now.
Yeah. Sorry.
Okay, it's just 1 minute.
You're very good.
As you can see, the first experimental test, and 50 kilometers, this train driving without the driver. The drivers are here, I mean 50 kilometers outside. And this is the project, TC Rail, as you can see. Honestly speaking, I mean, this can be done for cars, because I mean the challenges and the constant in railway are more than in vehicular communication. Thank you very much.
The question is, yeah.
Okay, Professor Ziad, thank you very much for your great presentation. And Mrs. Pia, we do the discussion in the end of the presentation of three speakers, isn't it? So we are now going to the next presenter, Dr. Andri Triwinarko. And before the presentation start, I will read the CV of Dr. Andri Triwinarko. This is his education: a bachelor in informatic engineering from ITB Bandung, the master in electronic engineering from Universitas Indonesia, and he get the double degree in master in informatics from UBS France. And the last one is also the former students of UPHF doctorate program in electronic from IMN 2A of UPHF of Valenciennes, France. Next, and this is his professional experience. Currently, he is a postdoctoral fellowship in Interlabs Research Laboratory at Department of Engineering and Computer Engineering. But Dr. Andi also already in Indonesia right now. And from 2005 until now, he's a lecturer and researcher at Polytechnic Negeri Batam, Indonesia. 2013 until 2016, head of Center of Research Communication Service at Polytechnic Negeri Batam. And the last, from 2011 and until 2013, head of Department of Informatics at Polytechnic Negeri Batam. And here is the several research experience that I put in this presentation is just in area of vehicular communication from 2021 until 2022, as I said before, is postdoctoral fellowship. And then the performance of radio access technology had achieved for next generation vehicle of to portable road user network. Also from 2021 until 2022, BMagnet, a cross-layer design for vehicular ad hoc network, VANET. I think this is his dissertation research from 2016 until 2021. Internet of Things for healthcare application, VANET challenge in Mac layer 2022, and the last one, sensor network 2018 and 2019. I think there is a lot more his research. There is just several research from him that actually related to vehicular communication and IT. And for Dr. Andy, the stage is yours. Thank you.
Yes, thank you, Mr. Gary, for the opportunity. So first, let me share the screen first. So it is shown in the screen now. Moderator, is it shown in the screen, the presentation
Yes,
slide?
that's a good.
Dr. Andy,
Yes, that's
we
right.
don't hear your voice. Excuse me.
Can you hear me now?
Yes, already.
Okay, thank you very much. So good afternoon, everyone in Indonesia, and also good morning for everyone in French. My name is Andi Trivinarko, and today I would like to present to you my research with the title The Vehicular Communication using the novel EEE 802.11 BD. And first of all, I would like to say thank you very much to the BRIN for giving me the opportunity to present my research in this webinar. So here are the table of contents of today's presentation that mainly will be divided
Dr.
into...
Andy.
Yes?
I think he cannot hear us also.
Yes, can you hear me now? Hello?
We don't hear you.
Yes,
Can you hear me now?
yes, your voice is good, clearly.
Okay. But anybody say that, somebody said that my voice isn't clear. Everybody can listen.
So I don't know, but in the BRIN office in the Tamrin, Jakarta, center of Jakarta, it's a good your voice and clearly. Thank you.
Okay.
I receive clearly.
Yes. So I continue the presentation, I think, now. Here are the table of contents of today's presentation that mainly will be divided into parts. The first part will consist of the introduction of the vehicular ad hoc networks, or wait, I received a call from Gali. Wait. Yes, hello? Yep. Gali. Iya. Coba dites lagi ya.
Pak Andi masih di mute, Pak.
Ups. Halo?
Ya, sudah terdengar, Pak.
Oke, terima kasih Mbak Pia. Yes, the first part of the table of content will consist of the introduction of the VANETs in the context of the intelligent transportation system, and also we will discuss about the state of the art of the VANETs and also the problem statement of the existing 11P standards. While in the second part, we will discuss about the experimental research, which consists of the preliminary results and also our contribution of using the cross-layer design for the new standard of 802.11 BD, Next Generation Vehicle to Everything or NGV standard. And finally, we will discuss about conclusion and the perspective. So what is VANET? Well, basically, VANET is a continuous and high-speed data communication between vehicle to vehicle or V2V, vehicle to roadway infrastructure or V2I, vehicle to pedestrian or V2P, and also vehicle to cellular network or V2N. VANET is also known as the vehicle to everything or V2X communication. As stated by Prof. Iyad Dayit before, that the appearance of VANETs can be used to support the development of the Intelligent Transportation System or ITS. So why is VANET important for Intelligent Transportation System? As we know, there are the classical problem of today's transportation systems, such as the road accident, the traffic jam, and also the environment problem or air pollution. Here are some statistical data about the transportation problem, where according to the World Health Organization, around 1.35 million of people die to the road accidents, or every 24 seconds, someone dies on the road. Road accidents is also the first cause of the death among children of 5 until 14 years old, and also young people of 15 until 29 years old. According to the mobility scorecard by INRIX, in the United States, the driver lost around $88 billion and around 99 hours due to the traffic congestion, while Paris is ranked number 7 as the most congested city in the world, where drivers spend around 165 hours per year on the traffic jam, with the average speed of only 10 miles per hour. So here are some highlight example of the VANET application use case for the Intelligent Transportation System. The first one is the famous Smart Autonomous Car by Google, also known as the self-driving cars that already implemented. There are also platooning application that already explained by Professor Iyad Dayit before, where several cars travel together in the road. And here are some vehicle to everything solution from uBlocks. uBlocks is a company in the European that produce chip for the vehicle to everything solution. He creates some applications such as the crash prevention system, such as the blind spot warning, emergency electronic brake assistant, and also cooperative forward collision warning. They also produce the driving assistance system, such as a lane changing assistance, left-right turn assistant, intersection movement, controllers vehicle warning, etc. And there are also another type of vehicular communication applications, such as a traffic information system and also internet and multimedia in the cars. So now I will play you the small video from the Tesla company. We will see the famous application of autopilot from Tesla to have some insights of more about the existing intelligent transportation system application.
Tesla Autopilot. It's the most well-known driver assistance system in the world, and its features have impressed millions.
So we can see here the driver
it's even more impressive than meets the eye.
Wheel, so the car will,
when people think about autopilot, they tend to look at what it can do. It can keep you within a lane, even in tight curves. It can adjust its speed to match the car ahead of you. It can change lanes on its own. It can take highway exits on its own. You probably already know all of this if you've ever used autopilot, if you've witnessed it, or even if you just looked into it online. Now, this stuff alone is incredible, and it's enough to amaze almost anyone who gets to see it in action, but trust me when I say that this is just the tip of the iceberg. The key to seeing how impressive autopilot actually is lies in the smallest details. In February of 2020, Tesla released this 30-second clip showing an example of what the forward-facing autopilot camera sees, along with all the annotations made by the computer, which demonstrates what the system understands about the world around it. Okay, so at first glance, it looks pretty complicated, but also pretty cool, right? Let's take a closer look at the details. Let's start with these arrows on the road. Now, we've all seen these before, indicating which way you can turn, but look at how they're labeled. LA, FA, and RA. That's left arrow, front arrow, or forward arrow, and right arrow. These are correctly labeled by the system. If we keep advancing, we can already see LA, FA, and RA in the distance. Now, if we move closer, it reveals that those are correct annotations of each arrow. If you're not impressed yet, just remember that this is a computer recognizing arrows on a video that it has never seen before. Alright, let's talk about stop signs. Now there's a stop sign coming up, as you can see here in the intersection, but if we rewind to go see where autopilot first saw that stop sign, we can see that it actually found it really far back, all the way out here. If I can find this frame, and if we zoom in, we could see that stop sign labeled and outlined in red. Now, if we keep going, as we approach the intersection, we can see that not only is the stop sign labeled, but the line where the car should stop is also labeled with a red line, as well as the letter S for stop. Over here, we have another stop sign coming up, and as you can see, it's labeled with the red outline as well as the stop line. And even though that truck was there, it still managed to properly label the stop line. Pretty impressive.
So yes, from this video, we can see that how Tesla see the environment or the surrounding area. And what is the most impressive thing about this one is that all is doing in the real time. The camera will capture the image and then processing, and then the car will decide it how to move based on the real-time calculation. So of course, if we want to implement this application, it's not only about the telecommunication part. We also need to study, for example, about the image or video processing, or also using artificial intelligence, how to recognize some object, and then of course the telecommunication part, how to make the communication between the vehicle or the car with the environment will be good. So now I will continue to the state of the art of the existing standards. So basically, there are two existing radio access technology, or RAT, for the vehicular communication or VANET. The first one is based on the Wi-Fi technology called Wi-Fi V2X, and the second one is based on the cellular technology called cellular V2X or CV2X. The Wi-Fi standard is issued by EAAA and called 802.11p standard, while the cellular base standard is issued by 3GPP and called 4G LTE V2X. The 11V standard in the United States is called Wireless Access Vehicular Environment, or WAV, also known as Dedicated Short Range Communication, or DSRC, while the 11P standard in Europe is called the Cooperative Intelligent Transportation System, CITS, also known as ITS G5. The focus of the research will be mainly on the Wi-Fi based V2X. So yeah, these are the comparison between the European and the United States standard. These are the stack protocol of each standard. Basically, in the physical layer, they use the same 802.11p standard. A little bit difference will be in the MAC layer, where the European standard will use the decentralized congestion control, or DCC MAC scheme, while for the United States standard using the multi-channel MAC scheme. And also the standard protocol used is different based on the organization that issued the standards. So VANET having the characteristic of highly mobility of the vehicle or cars, rapid change of topology, and also intermittent connectivity and predicted path. Here are the challenges of VANETs in each protocol layer. For example, in the radio propagation model, we need to consider the signal attenuation problem and VANET's environments such as a rural area, urban area, or highway environments. And in the physical layer, we need to consider several problems such as the interference, coverage, and bandwidth utilization. In the MAC layer, we need to address several problems such as the blocking problem, exposed and hidden nodes problem. While in the net layer, we need to consider whether to use the broadcast unicast or multicast or maybe geocast communication. Basically, different VANETs application needs to different type of quality of service or QoS. So here are the VANET standard evolution from the family Wi-Fi standard 802.11. The first VANET standard is issued by IEEE in 2010 called 11P, which operating in 5.9 GHz frequency band, having a data rate from 3 to 27 megabyte per second using OFDM modulation with a channel bandwidth of 10 MHz. While the latest Wi-Fi standard is called 11AX, or we also known as a Wi-Fi 6, is issued in 2019, operating in 2.4 or 5 or 6 GHz frequency with the data rate up to 10 gigabit per second, supporting the multi-user MIMO and also OFDM multiple access or OFDMA, having a wider channel bandwidth up to 160 MHz. Recently, IEEE formed the new task group called TGBD to create the new standard of 11BD, which is the enhancement for next generation V2X NGV of legacy 11P standard. And the standard is expected to be issued in 2021. So what is next generation V2X or NGV or 11BD standard? Well, 11BD is the modification of the 11V legacy standard for future next generation V2X application. According to its project authorization request or PAR, 11BD standard has several objectives such as having 2 times higher throughput, operating in high mobility channel with relative speeds between vehicle up to 500 km per hour, having a 3 dB lower sensitivity level, which means having extended communication range, and also providing interoperability, coexistence, backward compatibility, and fairness with deployed outside of the context-basic or OCB device using 11P legacy standard. So now we will discuss about the problem statement of the existing standard 11P. In this research, the objective of the research is to improve the performance of VANET application for 11BD, and the key objective is having a reliable transmission by minimizing the packet error rates, and also having a better network performance by improving the data throughput. The research methodology used the modeling and simulation method, where we evaluate the cross-layer design at VANET environments with high mobility. So in this research, we built our VANET simulator using a MATLAB and wireless LAN toolbox, where the transmitter will have a physical service data unit and then generate into waveform that comply with the 11P and also 11BD standard. Then we send this waveform into P2P channel model and adding the additive white Gaussian noise. Finally, the receiver will do the channel estimation and also channel equalization and decode the received waveform to obtain the physical service data unit at the receiver. By comparing the PSDU both at the transmitter and receiver, we will have the packet error rate. For the V2V channel model, we use the channel model using tag delay line model proposed by the 11DSRSC group and also ETSI ETSG5, which have 5 environments such as the rural line of sight, urban approaching line of sight, highway line of sight, urban crossing non-line of sight, and also highway non-line of sight. So here are the first problem statement of the legacy 11P standard. We can see here the performance of the throughput will be depend on the packet size or payload size, and also the modulation coding scheme that used in the system. A bigger payload size and higher modulation coding scheme improve the throughput for performance. On the contrary, a smaller payload size will reduce the throughput efficiency due to the packet preamble overhead. The second problem statement will be the impact of the vehicle density. As we know that the 11P MAC standard using the carrier send multiple access collision avoidance or CSM-ACA protocol, which forbid a simultaneous transmission within the same radio range to avoid the interference and collision. We can see from the picture here where when vehicle 1 want to communicate with the vehicle 2, all the vehicle within the communication range, such as the vehicle 3 and vehicle 4, will be a block or called the divert node, so it cannot communicate with another vehicle. So in high density VANET, which include a lot of vehicle, the problem will get worse because a lot of vehicle will be blocked. So we can see here the performance of the throughput based on the function of the number of car. The more dense the number of the vehicle, we can see that the throughput will be reduced.
Now,
so now we will see the experimental results. So the motivation behind the research is that 11P, as we know, is a robust and mature technology. On the other hand, the Wi-Fi standards are evolved, and 11BD was formed recently to explore the future roadmap for the next generation V2X. We would like to investigate the physical layer enhancements from other 802.11 Wi-Fi standard to improve the performance of 11P standard. So here are some key features of the physical layer enhancements. As we can see here, the 11P standard is still using the binary convolutional channel coding, while we can use the new standard using the low density parity check channel coding. And also we can consider another technology such as mid-ambulance channel estimation, extended range mode, or dual carrier modulation, MIMO using the space-time block coding, using the multiple spatial stream. From all the key features above, here are some hypotheses that we can be used to improve the performance of 11BD. For example, using the LDBC and mid-ambulance channel estimation will give a better channel estimation. Using the extended range and dual carrier modulation will improve the reliability and also the communication range. And using the MIMO space-time block coding will improve the throughput using a multiple stream. Here are the simulation parameters that used in this research. And we choose two performance metrics, which is the packet error rate and also the throughput in the MAC layer. So we can see here our proposed technology, such as using the dual carrier modulation, or also using the extended rate, and also using the better channel estimation using LDPC channel coding, and also mid-ambulance channel code will mid-able channel estimation will give the best performance compared to the 11P legacy standard. We test in this two environments, which is the rural line of sight and also highway line of sight, where the rural line of sight is considered as the slow mobility environment, and the highway line of sight is considered as the high mobility environment. And also for the throughput, we can see here the performance will be better compared to the legacy standard, except for the dual carrier modulation. It gives the worst performance because it sends the symbol twice in order to have having a good reliability. but in the other side, it will reduce the capacity of the data rate. For the high throughput application, it also gives better performance. Our proposed solution using the MIMO space-time block coding using 2 transmitter antenna and 2 receiver antenna, and also using 2 spatial stream will give the best performance compared to the legacy standard. So here are some preliminary result conclusion. LDPC and mid-embals are recommended for all V2X application because they can give a better channel tracking mechanism that minimize the packet error rates of the received signal at the receiver side. Dual carrier modulation and extended range mode are recommended for V2X application that need a higher reliability requirement, such as safety application, because they can give a better performance even in the worst signal-to-noise ratio condition. And finally, the MIMO technique using the space-time block coding is recommended for V2X application that needs a higher throughput requirement in the unicast transmission scenario. So now I would like to present our research contribution using the cross-layer design for the 802.11bd or NGV standard. So as we know, the motivation behind this research that the project authorization request or PAR of the NGV standard is asking us to propose another design to have a 2x higher throughput at the MAC layer, and also can operate in the highly mobility environment with relative speed between vehicles up to 500 km/h. So based on our physical layer enhancement before, we are proposing our cross-layer consideration design, where in the physical layer for the safety-related application, we choose to use the mid-embal channel estimation using the LDPC and mid-embals, and also dual carrier modulation. In the MAC layer, we are considering using the frame aggregation and choose the proper contention window size. And for the net layer, we consider using the broadcast and single hop communication. For the higher throughput or non-safety related application, other than the mid-embal channel estimation in the physical layer, we also propose using the MIMO space-time block coding using 2 transmit antenna and 2 receive antenna with 2 spatial stream. And we also use the frame aggregation in the MAC layer and using the retransmission limit in the MAC layer. And finally, in the net layer, we use the unicast and single hop. For the performance metric, we choose the normalized throughput at the MAC layer. So I will not go deeply in the mathematical part. Well, basically, we use the symbol error rate in the physical layer to calculate the packet error rates, and use this packet error rate in the physical layer to calculate the throughput in the MAC layer. So for the performance analysis in the MAC layer, we use the transmission probability using the famous Bianchi model, where we consider the condition of the channel will be, there will be some successful transmission. Also, there will be a probability of data error transmission and also the collision transmission. So we use the PER result from the physical layer to calculate the performance analysis in the MAC layer. This part we call it the cross-layer design. And finally, we use the normalized saturated throughput to calculate the performance metrics. Here are the simulation parameters that used in the simulation. We choose the enhanced highway line of sight because this one is a high mobility environment with relative speed between vehicle up to 500 km/h. So the improvement of the PER performance will affect the throughput performance in the MAC layer, because based on the cross-layer design in the throughput performance analysis, a better PER will increase the probability of successful transmission in the MAC layer. So here are the simulation results for the safety application. We can see in the ideal condition where there will be only 1 transmitter and 1 receiver vehicle. There will be no interference. We can have the improvement up to 205% or 2x higher throughput at the MAC layer. For the dense FANET, for example, here, if we use the contention window of 15, for the worst condition, for example, for 220 vehicle, which is more than the value of the contention window, we still have a 100% improvement. But when we continue to add the more number of the vehicle, the performance is getting reduced. Also, the same result for the non-safety or high throughput application. For the ideal transmission with only one vehicle without interference, we successfully having 2 times higher throughput at the Mach layer, which is around 204%. And yes, the same performance will be reduced when the number of the vehicle will be reduced. So here are the conclusion of the research. Our proposed solution using cross-layer design can address the project authorization request of EEE 802.11 or MGV standard, where it can operate in high mobility environment with maximum relative speed up to 500 km/h, and also achieve 2 times higher throughput in ideal transmission, only one transmission without interference, for both safety and non-safety as requested by the project authorization request. For the perspective, we need to investigate another objective by the NGV PAR, such as the achieving at least one mode transmission having a 3 dB lower sensitivity level or having more extended communication range. Using maybe we can achieve that by using the dual carrier modulation and also extended range mode. We also need to consider another performance metrics such as latency and delay, and also the new standard 11BD considering to use the millimeter wave or 60 GHz for FANETs. Maybe we can use the potential beamforming technique to improve the performance. And finally, of course, after proposed using the cross-layer design, we would like to implement this proposed cross-layer design to a real FANET communication device using a software-defined radio and to the real-world test field measurement. This work has been published in the journal, in the Vehicular Journal, which is the quarterly one journal with the title of Physical Layer Enhancements for Next Generation V2X Communication, and also a conference with the title Performance of Physical Mech Cross-Layer Design for Next Generation V2X Application. It got accepted in the IEEE International Conference on Internet of Things and Intelligent System that will be presented in November in Bali, Indonesia. So thank you for your attention. Now we will go back to the moderator. Mr. Gali, please.
Okay, thank you, Dr. Andi, for your good presentation. Actually, I have several questions, but I will keep it in the end of this event. And we're going to the next presenter, the last presenter, Professor Elhad Dogesh. And here is the CV or our last presenter. Professor Elhad Dogesh, he had the BSc from University of Science Technology Lille, France. Also for MSc and also for the PhD. And here is the several of his research experience. Pardon me, sir. Perhaps I would like to read your CV, or no problem. If you want to tell about yourself.
No, sorry.
Okay, thank you, sir. Excuse me. To the committee, please share again the CV of our last presenter, Professor Elhad. Thank you. And here are several of his research experience: International Joint Laboratory with NUS Singapore, Nanyang Technological University, IELTS and CNRS, for the application of nanotechnology for novel architecture of microelectronics and photonic device. And he also published over 120 papers in international journal and research conference. And he is also a senior advisor for Indonesia Affair at UPHF. And he's an honor for him. The expert in 2011 and 2012 for French Ministry of Research and Higher Education, ASEAN, Development Countries General Management for Research and Innovation Workshop, participant and contribution on thematic ICT and nanotechnology, expert CNRS in 2010 in the working group Advanced Photonic Technology, and 29 and until 2018 as our Singapore Research Project, and also he's expert for Saudi Research Agency, HT Riyadh, Saudi Arabia. For Professor Dogesh, the stage is yours. Thank you.
Thank you very much, Gali. Salam alaikum to all of you. It's a pleasure to show you our activity. And okay, so this is my first of all, I would like to thank you for inviting me to this webinar. I have a pleasure to show you the main activity in our institution, our university, our technopark. I would like to say that last June we had the chance and we had the honor to host the joint working group between France and Indonesia. Many researchers, professors, rectors, high decision makers from Indonesia attend, and from BRIN also. And I would like to take this opportunity to thank the French Embassy with Stephanie Claudia, who is connected now. Thank her for organizing with me, and thanks all the delegates from BRIN who attended, including Dr. Andoko, all of you, all by your names. So my talk will be just to introduce how the technology can be as innovated as possible for transportation of the future. So just to indicate you that our University Polytechnique Hauts-de-France is located in north of France. We are belonging to the CNRS. CNRS is like BRIN. It is National Research Council that is gathering all the labs for the whole France. We have more than 8,000 labs in France for different fields, and we have more than 40,000 researchers. And just to indicate you, last week the Nobel Prize has been given to one member of CNRS. He was working on quantum physics. CNRS is one of the biggest institutions in Europe. And we are also a member of the European Alliance. So just to indicate you that we are in the top of France, Hauts-de-France in French, Hauts-de-France and Valenciennes, you see, we are in the middle. Just to indicate you, historically, our area is an area of heavy industry. More than 100 years ago, where this Valenciennes was the area of heavy metals production. But using metal, people start to fabricate cars, railways. So that's why now Valenciennes is one of the leading area in Europe, in France and in Europe also, for the production, for the innovation in railway, in automotive and railway technologies. We have more than 150,000 workers in this sector, in this field, and we have the three major companies of automotive cars like Toyota, Mercedes, Renault, and Fiat. And we have also the two major companies in railway like Alstom and Canadian Bombardier. Of course, I said you historically 100 years ago we are producing metals, but you should understand that we have developed an ecosystem step by steps. Since 30 years, we have developed an ecosystem in the campus with one section dedicated to training, one section dedicated to research lab innovation, and one sector dedicated to companies, startup, clusters, and technoparks. So if you visit us, you will see the whole link between education and till industry. So the technopark, it is Transalé. It is a technopark, and Transalé, this is just a contraction of Transportation Valley. So Transalé is a technopark dedicated to technology for transportation. I will just show you. So if you see the technopark, it is 40 hectares. It is dedicated mostly for transportation, for mobility. Every mobility, not only transportation, can be mobility in hospital, mobility in the city, mobility. I mean, the whole aspect of mobility.
I'm sorry, Professor, I interrupted. You can full screen the presentation?
My presentation is not?
Not yet.
Oh, because I put my presentation. Oh, I'm sorry. So you don't see my presentation from the beginning?
It's in.
We have, but
My
you
presentation is in
are
the...
not full screen.
Oh. Oh. Is it okay now? Is it okay?
Yes,
Yes,
it's
sir.
clearly.
I'm
Very
So-
good.
So maybe I restart very quickly, okay?
We can see, but not in full screen.
So I can start. Okay. So I mean, so Transalé is Transportation Valley. We have the map of the campus for ecosystem in railway, automotive, and eco-mobility fields. Just to say one of the aspects of the mobility, it is the Institute IMTD, Institute of Mobility and Transportation Development. So this is actually, you have the website. This institute is dedicated to mobility, I mean, with different goal to promotion of the for industry, the networking, the innovation, and the encourage the discovery, specifically for the young generation, for the future human resource. Okay. So what Transalé, just briefly, you can see the website, you have all the information. One object, two players. In fact, the campus is included in this project because we IMTD is institute at the service of the student, of the industries, and of the researchers. So I mean, in the campus, we have a large campus which brings the university and the Technopark Transalé to work together. Okay, so we are working for the innovation and the future of mobility sectors. Just to let you know why, because the area Hauts-de-France, Valenciennes, is actually the very, very nice situation in Europe, in the heart of Europe, with many situations close to Germany, to London, to UK, to Belgium, to Holland, to Germany, to Paris. So we are, I mean, we are very, really nice, have a nice situation. Sorry. And of course, the student, I mean, the student, master, PhD, and bachelor degree student, they have a main role in this activity because they are working on some project. They are participating in the techno ecosystem dedicated to transportation. So the Technopark is at the service of the young generation to push them to share this activities and maybe to work in these activities for the future. We have many facilities. You can see in the website, but many facilities. We have laboratory simulators. We have some experimental on the top of the figure. You have some experimental labs to test the cars, to test any vehicles. So this is a very nice tools that is offered to industries and students. Just to mention, in our labs we are covering all the fields, electronics, telecommunication, but also mechanics. Just one example, in the campus, we have an industrial wind platform, just a small picture. The wind platform is used for transportation. You can test, I mean, the different characteristics of cars, in the field of transportation, aeronautics, environment. And just to let you know, the wind has a speed, maximum speed of 200 kilometers per hour. So it's very interesting tools that can be used for any collaborators. and some example of project that been used in the WIT platform for railway specifically here. Okay, so Trasale actually is a really nice technopark dedicated to transportation. So my topic is to indicate you how the new technology for communication can emerge in the near future. So I would just show you one example of study we did how to develop Li-Fi technology. Li-Fi technology, actually, it is known by only few people in the community because now everyone is using Wi-Fi, wireless technology. Li-Fi is using light instead of electromagnetic wave. So just to say you, Li-Fi has been first introduced by Professor Harald Haas from University of Edinburgh in Scotland. I had a chance to meet him. If you see the picture top right, I had a chance to meet him in Paris during an international conference on Li-Fi, and he's a very nice person. And he had the idea to use LED to lightning technology, but to transmit the data, I mean, to transmit with very, very high data rate. Why Li-Fi is a good technology? Just briefly, compared to Wi-Fi, Li-Fi has the advantage to have a faster transfer speed, to be non-toxic. I mean, the electromagnetic, there is no electromagnetic field, so you can use it in any field without any perturbation. And it's cheaper. You can develop your own local communication networks. I mean, if you imagine a city, a building, the city,
your screen is not moved from the last slide about a unique location with a multiple function. That is the last screen that you shared to me.
So
I don't know what happens. Let me check. Excuse me, sir. You should. Yes. Okay.
Is it okay? Is it okay?
In my screen, it's still a freeze.
Is it okay for the screen?
Check, please. For the other participant, is there the screen is moving? Because in my laptop, this is freeze.
No, freeze.
Please tell.
In here
This
also
is
freeze.
the page of
Still freeze, yes.
Still freeze.
Yes, still freeze in my laptop.
It's
Yeah.
still in the page of
Yes,
A unique location with multiple function. Yes.
Is that right?
It's still freeze.
I can. Okay. Can you download again? Maybe.
Okay.
Maybe stop again.
Yeah. Okay. Okay. This is my Zoom.
Begin again. Yes.
Because instead to restart the sharing.
Oh, this one.
Yeah.
Oh, maybe I built.
It's okay. It's okay. I don't know because I don't touch anything. I am very careful. I just speak. I'm not teaching. Is it okay now?
Yes.
Yes. Okay.
Yeah. I'm sorry.
Yes.
Gali, come. Full screen. Thank you, Gali.
You're welcome.
Is it okay?
Okay.
Okay.
Please move one page to test.
Okay. Okay. So Li-Fi. Okay. Just restarting. So Li-Fi technology is a very emerging technology. So Li-Fi has been introduced by Professor Harald Haas from University of Edinburgh more than 25 years ago, more than 25 years ago. So the main aspect is to use LEDs, lightning technology, but to transmit high data rate. What is our objective? Compare Li-Fi to existing Wi-Fi. Li-Fi has a faster transfer speed, more than 1 gigabits per second. It's the cheaper technology because you don't need license. It's very interesting point. If you use Li-Fi, you don't need to use a specific license, so you can create your local license in the company, the manufacturer, in the city. So it's very interesting. it's a very low energy consumption, and it's a point-to-point. And one of the main aspects, it is not it is secured communication. It's a highly secured communication. So Li-Fi compared to Wi-Fi has many advantages. Just two small pictures. If you use Li-Fi, you see you have the light and you have the propagation of the light in the room. And so if you are under the light, of course you have communication. If you are outside, you have no communication. So it's one aspect of security. Just to indicate you one remark, I have a friend in US, and he said me that in Washington, in the Oval Room, the President of the United States, actually he's still using the telephone with a cable. I mean the old technology, because they are afraid that using cell phone, the communication can be kept by some spy or by a hostile country. So they are looking for new technology. Li-Fi should be a good technology for the future, for the actual president of the United States, and maybe all the presidents. Just, of course, Li-Fi technology is based on a specific device. This is the LED, the source and the detector. Actually, the LEDs, all of you are probably using LEDs technology. It is standard technology. It's very, very low frequency and very big element. So our objective, how to miniaturize, how to increase the frequency for the transmitter, the LED, and also for the receiver, the photodiode. Actually, if you look the Li-Fi technology, one of the objectives is to reach a rate of 10 gigabits per second, or maybe using laser we can reach 100 gigabits per second. This is the objective that every groups in the world are trying to obtain. How does it work? Of course, you have the light here on the right. Is it okay? You have the LED lamp, you have the photodetector. So this is the main. And of course, you need to connect the light to the server, to the cloud, to the router. I mean, to the informatic structures. So this is important. Of course, the advantage is the efficiency, availability, capacity, and security I just mentioned. It is a nice and so Li-Fi can be used, of course, for the city, for example, for the light, smart lighting, for the control of the traffic light, for the communication between cars. That's why I consider that the Li-Fi can be used in the cars, in the front light, can be used as an emitter, and we can imagine communication between two cars in the traffic, in the road, or maybe the cars and the city, installation station in the city. Of course, Li-Fi can be used for underwater transport, for as you see in the screen. So can be used also for maritime technology, for maritime traffic. Of course, it's not the transportation, but I would like to also introduce that Li-Fi is maybe the future for the hospital. We can imagine tomorrow the light is, of course, during the operation, the medical operation, the doctor, the specialist can use the light to, of course, to light for the room, but also the light for the communication between his instrument and the platform. So, and this without any perturbation, any interaction with the instrument. It will be a safe protocol. Just to introduce that we have developed this topic of health technology using Li-Fi. We have developed this technology with one of our PhD student from Indonesia, Untuk. He has been graduated in March 2012, and we had the support from Nusantara program from French Embassy, and specifically from IFI during the years 2018-2022. And actually, we have the visit for 3 months from Mr. Gali Nourkafi from BRIN in a high-level scientific stay, also funded by the French embassy. So, I mean, we can develop some technology with the support of our partners in French embassy, from maybe, I hope, from all our partners from all around the world, and particularly with BRIN in Indonesia. So for airlines, we can consider that the Li-Fi can be a good technology, for example, in the airplane to overcome the problem of communication media during the flight. So we can think that it should be a very good tools to propose some new services to the passenger. Of course, the main problem is, as you see in the picture, the LEDs are very big elements. I mean, more than 10 centimeter size. And so it's not possible to use the actual LEDs for high data rate communication. So it is necessary to work for new design, new process of fabrication, appropriate packaging and prototyping of new LEDs. So this is what we did in our labs, our institute. We have developed some innovation for light fidelity, innovation in terms of material, of design, of clean room technology, and prototype. Just our labs is IEMN, Institute of Electronic, Microelectronic and Nanotechnology. We have the mission for education, master and PhD and postdoc. We have the mission of research to develop new research, but also we have the mission of innovation and support to economic partners or industrial partners. This is just a small view of our lab. We have 500 people and 250 permanent position. We have the policy of 30% for long-term research with basic phenomena and innovative solution, 50% for midterm research for designing, fabricating, characterizing microsystem and microelectronics and telecommunication, and 20% of our activity, of our policy, it is to answer to industrial needs. So actually, we have the chance to use to have 4 platforms. One is the clean room dedicated to micro nano fabrication. One platform is dedicated to microscopy. One platform is dedicated to the measurement facilities, and one platform is dedicated to telecom. This is a view of our clean room, so we can fabricate any devices for transportation of the future. We can fabricate sensors, generators, and I mean, any sensors can be fabricated and designed in our institute. This is a view of the characterization room. For each platform, we have the chance to have some permanent engineer, technician to help us to develop our technology and to do our experiments. This is the near field platform. We have also some staffs. And this is the telecom platforms. So just to let you know that we have the facilities for any of our partners in Indonesia to develop some technologies together. So our motivation is how to increase the bandwidth for the Li-Fi technology. Of course, to reduce the bandwidth in the microelectronic fields, it means reduction of the size, reduction of the capacitance. So first step is to select the best materials. So we have, of course, we have identified gallium nitride technology, which is the basic materials for LED technologies. And so the challenge was to make the groove, to optimize the groove parameter, to design a fabricated micro photodiode, and to characterize the devices, static and dynamic characterization. This is just one example of the clean room. If you look in the right, this is my daughter. She has a chance to do an internship in my lab. So I try to introduce her to Li-Fi technology, to clean room. But unfortunately, she decided to do cybersecurity and big data and so computer science. So I failed my mission. But anyway, cybersecurity is also very good. So the roadmap we have decided for this study to develop Li-Fi technology was to first to investigate which configuration of materials we have to do. I mean, we have investigate MBE, molecular biomethylpetaxy, or MOCVD technology to grow the material. to make the characterization, to study the composition. Phase 2, we have investigating the etching process for the photodiode, for the laser, fabrication of different size of photodiode, micronic, nanometric, and to characterize, of course, the devices with current, photocurrent, efficiency, and the frequency with the capacitance, frequency bandwidth, noise measurement. This is typically the PIN structure we have developed. So we have developed a multi-layer quantum well structure. For the materials, we have decided first not to produce by ourselves the materials because it takes time to optimize. So we have decided to contact some partners. Sorry, we have decided to contact some partners from Switzerland with Novagan, from KAUST in Saudi Arabia, King Abdullah University of Science Technology, from Singapore, A-STAR, and from Korea, KAIST, Korean Advanced Institute of Science Technology. So we have compared the characteristic, the performance for 4 different providers. So we have, of course, we did some characterization of the microstructures with AFM to observe that the materials was good enough in quality. We had designed a roadmap. We have fabricated and designed and fabricated large-scale photodiode, 100 micron, and micro scales, 5 micron. And of course, the objective is to reduce to a few nanometers and to reduce the active surface and, of course, to reduce the capacitance. And we typically this is the design. So we work during a few months to develop a design. So for static characteristic, we have developed just a capacitance structures. If you look the design of the mask, and on the right, this is the design for microwave application. So if you consider here, this is the design. The signal is in red here, and the green is the ground. And if you look the center here, the small dots here in the center, this is our photodiode, 100 micron, and here this is 5 micron. So this is typically the design in order to obtain a very good device. Here, this is the roadmap for the fabrication in the clean room. So we have phase 1, phase 2, phase 3 until phase 5, corresponding to the different technological step in order to fabricate our micronic LEDs for Li-Fi. Of course, one of the main aspects in the fabrication of any device in microelectronics or nanotechnology, it is the etching process. So we work during a long few months to improve our etching process. You have a figure from the microscope, electron microscope on top right. This is the etching process of gallium nitride. And so because why we study the etching? Because it is a critical phase for fabrication of vertical device. We have optimized the process, ICP process, using gas argon and chlorure for ICP. We have select different type of mask, metallic mask, silicon mask, photoresist mask. And so we have obtained the good results as shown in the figure on top right. And we have published these results last year with this paper, just which is indicated here, development of micro-size photonic devices for deep gallium nitride etching. So this is all the views of the etching process with the different masks. We see that for photoresist mask, the results is not good. For ICL2 mask, the results is good and not good enough for us. But for metallic mask, the results is perfect. So that's why we have selected metallic mask for developing this Li-Fi technology. And here, this is the image from the fabricated LEDs for Li-Fi. On the down right, you have the final photo from our LEDs. So just consider that the LEDs, the LEDs is just the part in the center here, 100 micron and 10 micron here, and the rest, this is just the electrical connection. Of course, to measure the performance, we have developed some new process, new experimental technique. So to measure the photocurrent here, this is just one experimental view of the photocurrent. If you look the screen, you have the sample is in the center under the microscope, and we have connected the electrical wires here on and in red you can see the optical fiber and the dot, the light in the center. This is the technique we have used to characterize the LED. We can see better here. So you see here the photocurrent measurement. In the dark condition, the optical fiber don't eliminate the photodiode, I mean the LEDs, the device. We have no current. When you put the light in the optical fiber, we create some current inside the LEDs, the device. So it was very good experiment to estimate the efficiency of our device. So this is some example of curve. So we have measured the photocurrent created by the light is very important until 3 milliamperes, and the efficiency is more than 10%. So should be it's a very measurement for the cut technique, the noise measurement. So if you see here the down right the photo of the setup with the noise figure equipment, with the coplanar probe, with the lamp, with the sample, with the super zoom camera. So we have extract the response of our device under with the frequency. For large photodiode, I mean 100 micron, we have measured a frequency of 300 megahertz. But for smaller size devices, 25 micron, we have measured a frequency of 1.5. And recently, we have measured a frequency of 2.4 gigahertz for the diode of 5 micron. This is actually one of the best results in the literature. Of course, we have published these results also in Photonics Journal, IEEE Photonics Journal. Of course, as a perspective, we can imagine that tomorrow, if you have chance to have a car's ODE, we can consider, for example, the front light like emitters, producing the signal, and we can maybe consider the detector in the cars that receiving the communication. So we can imagine for the future a optical wireless communication between cars, cars and the city, the smart city. And this is my vision how Li-Fi can be a good opportunity for automotive sectors, for railway sectors, for aeronautic sectors, for also medical sector, hospital, and it has many advantages. But of course, we need to work more and more to develop more accurate prototype, to increase the frequency, and so we need. It could be a good example of collaboration with BRIN to develop this technology in the future. Terima kasih. Thank you very much, and merci beaucoup. Thank you again. Yeah.
Merci beaucoup, Professor Elhaj. And then we go to the next session. We will doing some discussion here. So if there are a question to our presenter, please you can write it in the chat, or you can directly ask by raise your hand. And there is already a question from Bapak Wahyu Pamungkas. Bapak Wahyu, should I read your question, or you will ask directly about your question, sir? Hello? Okay, then I will read it. This is the question from Bapak Wahyu Pamungkas from Institute Technology Telkom. Good afternoon from Indonesia, Professor Iya Dayub. It is an honor for me to be able to witness your presentation this afternoon. Will you please explain the advantage of NOMA multi-carrier over OFDM in overcoming the doubly selective channel, particularly when applied to high-speed train with large Doppler shift and diverse multipath? Please.
Okay. Can I Please speak on your computer. Yes. Yes, thank you very much for this key question, actually. No orthogonal multiple access compared to OMA, and in particular to OFDM, actually enable what we call power allocation and not frequency allocation. That does mean that users will share, all users will share the total frequency band and also the time slot, but they will be differentiated by the level of power. So users close to the base station, they will have, a small part of the transmitted power compared to the users who are on board of the base station. This actually will allow a very good spectrum efficiency and also a source allocation efficiency. Why? Because when we are under orthogonal multiple access techniques, we reserve the same resources for both communication sides, even if one of these sides does not communicate at all. It is not active, but they have the resources. Now, considering no orthogonal allocation, we will not reserve this resource to the side who is not active, first of all. Secondary, when we consider two users, one with a strong SNR and the other one, on board with a very low SNR, actually, when we will decode the signal on the board side, we don't have the interferences from the strong one because we are coding the received signal on the board. The problem will be close to the base station, and when something is not
excuse me, this is a question and it's viewed in the screen up. Please back to the previous slide presentation.
Okay. Can I put this because I don't have battery on my. Okay. Yes. Or this one. Just one. It's okay. It's okay. Okay.
You still have battery? Yes. I don't have to put this.
The code script.
Okay, this is the session. Just a minute. Nine 9188.
The code, not
and the 5252 6935.
It's okay. Okay. So I will share the presentation. This is clearly done here. Yes. Do you hear me?
Yes, sir.
Hello.
Yes.
Hello.
Do you hear me, please?
Yes, sir. We can hear you.
Do you hear? Yes.
Yes.
I will share my
I share.
presentation now. Can I share the presentation, please?
You want to change? Yeah, just a minute, sir. Excuse me.
Okay.
How do you want to maximize? Excuse me.
Okay.
Oh, share screen. I think I should share screen. Excuse me, please stop this screen sharing first. Yeah, okay. It's already.
Is it okay now?
Yes.
We have already seen your presentation, sir.
Yes. Okay. Excellent. So, yes. So NOMA, as we can see here, I mean, this user is, I mean, a little bit far from the radio access point of the base station, and this one is just here. So the question is to allocate the power. So this one is, I mean, close. So the SNR here will be lower. I mean, will have, I mean, less power than this one. And now the access will be done here. So we have all the bandwidth shared between the users, all the bandwidths. But the first one, I mean, user, this one, of course, will open a small SNR. This one, the close, the biggest SNR part of the transmission part. While here, I mean, we share the frequency in OFDMA. So the first one will have the same bandwidth like the second one, even if he is poor in SNR. So it's a waste of resource allocation. While here, the two users have the total bandwidth, but one is stronger than the other one. So this will create another problem, I mean, interference is a problem, and we can solve this problem while dealing with, I mean, signal processing. As we can see, no need to estimate this user to detect the user one. The signal is directly detected, but here the signal of the user one will be detected and will be using 6 serial interference cancelers, will be of course subtracted from the received signal to estimate user one. It's not difficult, and we accept to do this treatment. On the other side, we will, I mean, we will win in efficiency, like we can see here. Per this NOMA will give 4.4 almost beat per second per hertz, and for the second one 74 compared to the orthogonal technologies. We have almost 45 up to 60 to 50% of I mean more resources. So this is why we use NOMA. Now, regarding the second part of your question and the channel environments or impairments, sorry, of course, the problem will, we are, I mean, tracking this problem now. And the question is how to deal, how to use NOMA while considering these, I mean, specific constraints related to the speed. Indeed, we are about to use adaptive serial interference cancelers. And by the way, this serial will impose what we call channel estimation first of all, and tracking channel estimation. And if you, I mean, we can maybe we can do a technical presentation here. We can see this work, I mean, on the error rate performance of full duplex cooperative NOMA in wireless. And I mean, this is how and this also survey codebook design for millimetric wave in both low and high mobility, how to do channel estimation while considering doubly selective channels. So I don't know if how indeed using iterative solutions and using what we call, I mean, adaptive channel estimations, and also we make use actually from the specific environment. Always we have a small, I mean, what we call CSI. We have some information about both road environment and railway environments, and we make use, of course, from database geo-localized stations with the inner and the previous decisions. And we have always an idea about the channel state information, and this will enable us, of course, to do what we call this codebook design for the transceivers, because we know and we can know if we don't have the channel state information, we can send first of all to train the network and to have the feedback and to make use. And of course you will see intelligence artificial, you will see deep learning, you will see for example machine learning based automatic for wireless. Donc, of course we make use of machine learning and deep learning to estimate our channel. And I don't know if I answered your question.
Okay, Doctor. I'm sorry, Bapak Wahyu Pamungkas, is that answered your question? If you have another question, I think you should we be doing in another session, because it's already late now, and now I have to go to the next question. Okay, this is the second question for Bapak Sasono from Research Center of Research Center for Electronic Grid. And the question is, we have been developing PLC systems in 2016, and we found problem on the controller and noise reduction. Our team is starting to using FPGA to cope the speed. Oh, I'm sorry. It's FPGA to speed as well. Is there any research
regarding this term in your university?
Okay.
So the question is about
the noise reduction in
of course, yes, please.
This one.
We actually hopefully I will have access to the slide. Otherwise, you know, when we are working in this hostile environment, in particular in cars, in trains. In trains, for example, we have the contacts between the pantograph and the container, which will create some arcs, electrical arcs. This will modulate the noise nature. In general, in transmission, we consider or we work under the Gaussian nature. We consider Gaussian nature in order to facilitate the treatment. So we have the two statistics, first one, the mean and the variance of the noise. But when we have this arc, this electrical contacts, by the way, we have these also inside machines, in cars, in also medical environments. The noise will be impulsive and not Gaussian anymore. And in that case, we must reduce the noise in order to to do our treatments. So one, you want to share? Yes, please. Just give me. I will show you what we collected this. We measured this onboard TGV at 280 kilometers per hour.
Visible light communication.
Okay.
It's not detected in my.
Okay, Vince.
I can.
No problem.
It's not detected in my computer.
Sorry,
You can.
It cannot connect to my computer.
Dr. Sasono, just to reply your question. Just to reply your question.
Pak Sasono masih ada, Pak Sasono? Mas Tino, Pak Sasono masih di tempat, Pak Sasono?
Yes, sir. I'm so sorry. I'm now on riding to go back to my home. I'm on a bus now. Hopefully someday I will write to you asking about the problem you're facing so far. And
very okay, can talk.
Okay, sorry. Okay, anyway, I'll put down email to you, and of course I will ask about how to solve the problem we found so far regarding the communication with LED lights.
Yes. So you mentioned LED lights in front of car. So definitively, if you mention the noise reduction, it's important to study very carefully the emitters. I mean the device, to select and maybe to develop some specific devices with low noise, because I mentioned in my talk that we did some noise characterization. So first step is to really identify, focus on the device, the front emitter, the device, and of course also the detectors. So rapidly, this is my two point I can mention very rapidly. But we are working on this.
Oh, okay. Thank you, sir, for your advice. But actually, my intention is to develop a cheap internet connection for the people of Indonesia who, by using ordinary LED lights available in our market. So we don't develop the cheap LED. So difficult difficult in our circumstances right now.
Sure, definitively we can consider that point of view. When we are going to visit you in with Iyad and President Artiba, our rector, we are going to visit Bandung and BRIN from 25. We will be in Jakarta 25 November in Jakarta to sign the MOU, the agreement. And we will be in Bandung from 28 until 30 of November. So we hope we can visit you in Bandung, maybe in your platforms.
And Serta.
Yeah,
in
but
terms of
definitively for your
Kang Ira.
question, the question of device is important, as has mentioned my colleague Professor Iya. The question also of the communication, of the protocol should be also very major
Yes.
issue. Okay.
Yes.
Thank you.
Thank you,
Yeah.
sir.
Terima kasih.
Terima kasih.
Thank you, Dr. Sono, and
Yeah,
thank you,
yeah.
Professor Elhaj. And this is once more question from Bapak Wahyu Pamungkas. He would like to explore the possibility of cooperating with UPHF, especially for doctoral students, maybe for PhD, and doing research. It's from Telkom.
Andy is one of the, examples of very fruitful collaboration.
Let me see the question. The question.
From Dr. Wahyu Pamungkas.
We are open and with pleasure.
Yeah, of course, of course. You know, we are very we are very happy to develop some more and more interaction with Indonesia, with universities, with research institute. I mean, with BRIN. So definitively, yes, we had in the past Erasmus program with Bandung, UI. And Polytechnic Batam and Bandung. So definitively we can develop maybe a new program, European program with you. Yes. We can talk this during our visit. If you meet us in Bandung or Jakarta, we can discuss this point, no problem. For joint degree and joint master degree, PhD degree and joint research, definitively. And also engineering training courses. I mean, a global educational program. Okay.
Maybe we should do a long conversation to explore all about the possibility that we can conduct. Yes, we will be able to do that in Indonesia. And the two last questions before the question from Mr. Yusuf, I would like to read the question from Mr. Benny from Center Research for Testing Technology and Standard BRIN. This is a question to Professor Ian. Your presentation is clearly on communication system and technology in electric vehicular communication system. In your presentation, you talk about standard IEC. Could you please have experience on ISO standard 15118 series on EV communication? In Indonesia, we have adopted the ISO standard for EV communication, and we would like to hear further explanation about this.
Yes, actually, indeed, you are right. I focus my talk on European standards. That's normal because we are funded by Brussels and by European Commissions. But the solutions or the technologies adopted now here are actually the same. I mean, when we talk about 5G pillars, the three pillars are there. I mean, here or on the other side, ISO or in North America, the technologies are the same. And Dr. Andy Triwinarco, I mean, mentioned that clearly in the first three slides, and he showed, I mean, very excellent presentation, that the physical layer up to the MAC layer almost the same in both sides. Some modifications of the difference is about, I mean, as for me, about political and strategical issues and also industrial lobbying inside standardization organizations. But as for us as researchers, I mean, we are, I mean, adapted to work on the two sides. I mean, for myself, I'm adjunct at Concordia in Montreal, and when I'm there, I mean, it's very simple for me to switch on ISO because, I mean, the solutions, I mean, the technical contributions don't change. I mean, no matter for doubly selected channels or millimetric wave communications or channel estimations, I mean, algorithmic are the same, but we work here under European constraints and they're under North American constraints. I think in Indonesia, you are maybe Dr. Andy now you return back and you are more, I mean, than me. I mean, you know more the regulations in Indonesia. I think that you are close to the North American standard, actually. Yes, I think so. But for the GSMR, for example, that's mondial and no difference between the two sides. So I feel that the difference is not huge. Okay, we are, I mean, one side based cellular and the other side based Wi-Fi. So now everybody, including here, I mean, we are about 5G and 5G for ITS, and this is actually the reality now.
So that is a global standard, not very it's standard from Europe or North America. Okay. Dr. Benny, it's already answered. Next, I think I will give a time for Dr. Yusuf. Dr. Yusuf, you already reserved the time.
Okay, thank you. Thank you very much, Mr. Gali. Dr. Gali,
okay.
Yeah. Okay. Hey, nice to meet you, Professor Erhard and Professor Ayat, and also Dr. Andi. Salam kenal juga ya. Yeah, I think we already meet before, maybe a couple months ago when initiating this collaboration, and this very interesting today. We have the insightful and very interesting talk about you and the future technology about the communication. Actually, yeah, in the maybe Mr. Gali already remember a couple years ago I discussed with you about the visible light communication, LiFi, and currently Mr. Gali contact with you and they have he has experience to research together with you. It's very interesting. And maybe in the later when you visit Indonesia, I will give special invitation to visit another campus, another branch of the BRIN in the Tangerang, Serpong area, not in Bandung. As you know, before the Dr. Sasono already asked about the noise in the visible light communication and anything. Actually, our office in the Serpong. So maybe if you have time, visit Indonesia and we can make a discussion with in our office in the Serpong. Maybe that's all my comment. Yes.
Yeah. Maybe it's interesting proposal. Maybe can you just schedule or make the program?
Yeah, I think.
Yeah, our stay in Bandung. Yeah.
Of course, Mr. Gali, I will make a program. I think later. Yeah. Okay. Maybe thank you. That is my comment. And if I have a question, it's just I ask your comment regarding which is the best technology for the future vehicle communication, vehicle-to-vehicle communication between the millimeter wave and LiFi, with the many advantages in each other, disadvantages I say, in each other. So if you have comment, please give us insight and maybe for our challenge in the future. Thank you very much.
Excellent question. I think we can see this problem from 2 points of view. First of all, vehicular communications, I mean V2X outside vehicles, and and communications inside. Okay. As for me, I mean, it's difficult to answer this question now, but I mean, the organizations are working on, to be honest, on 5G NR and on 5G for vehicular communications. As I mentioned, it is actually an economical issue and really a strategic issue. And if you want, I will just give you this amount of money. So 430 million of euros.
Yes.
In ITS, intelligent transportation systems, from now up to 2030. Can you imagine? And 100,000, more than 100,000 jobs in this area till 2030. That's not me, that's European Commission.
Yes, yes.
And this is just the amount of money in Europe. So honestly speaking, vehicular communications now are more realistic. And actually we have applications like Dr. Andy has shown. I mean, Tesla and Volkswagen also, and Hope, and all this, this industrials, they have products, actually. They have already products. As for Li-Fi, I think I will not, speak on behalf of Professor Haj, of course. I think this could be very interesting for inside communications, inside, because we will solve a lot of problems. But for in between, I think we will, for a couple of years, we will stay in, wireless. Vehicular communications based 5G, vehicular communication. It's my opinion.
Okay, thank you very much. It's nice, clearly. Thank you very much. Thank you very much. We are waiting you in Indonesia.
I'm sorry, we cannot hear you, Dr. Yusuf.
Really? Oh, still mute? Hello?
You are unmute, but I don't know, we cannot hear you. How about another participant?
Maybe.
Are you able to hear Dr. Yusuf? Maybe Tevia?
Maybe the connection. Maybe the connection, Pagali.
The same problem happened again. I don't know what happened actually, but we can hear you, Dr. Yusuf. Hey, maybe we can continue the discussion with the other medium, such as email or chat, because it's almost 1 hour past from the actual schedule. Actually, there is a lot of people interested to doing discussion further. Yeah, okay. We are waiting you in Indonesia. Hopefully we can meet also in Indonesia to discuss a lot of things. And by the way, this is the end of the session.
Excuse me, Mr. Gali. I'm sorry. I have one question. I'm sorry.
Hour is not enough to understand all of these topics, but we have many chances in the future to doing some other webinar, perhaps conversation directly, or maybe you can also contact directly if you like to share your email contact, sir.
I have just one word.
You have one word. Okay. So please, Dr. Professor El-Hadj, please.
Yes.
It's a pleasure always to discuss with you, all of you, and to really amplify the collaboration with Indonesia. And we are visiting you next end of November with 2 objectives: to sign definitively the MOU, the agreement between Valenciennes and UP and BRIN, and also to discuss the opportunity to have a joint laboratory, joint research center dedicated to transportation. This is one of our main object objective is how to have a joint lab in Indonesia, in Bandung, for example, working together on transportation, innovation, technology. Thank you.
Thank you.
Thank you, Professor Elhaj, for the closing statement. And I will give back the stage to our MC, Mrs. Via. Your stage is yours. Thank you.
Oke, terima kasih. Pak Galih, apakah bisa mendengar suara saya? Mungkin terjadi kenal Perancis di sana, mungkin ya Bapak Ibu. Baik, terima kasih kepada Pak Galih Nugraha Nurkafi MT sebagai moderator atas kelancaran di sesi pemaparan dan diskusi di webinar hari ini. Semoga bisa mendengarkan di YouTube di lain waktu. Terima kasih juga kepada narasumber atas materi yang disampaikan. Thank you to all the speakers for the great presentation. Semoga menjadi sebuah pencerahan dan insight bagi kita semua. Baik, Bapak Ibu, terima kasih atas antusiasnya memberikan pertanyaan kepada para narasumber. Semoga mendapatkan manfaatnya kembali dari acara ini. Baik, Bapak Ibu, hadirin serta kawan BRIN yang berbahagia, alhamdulillah kita telah sampai di penghujung acara. Terima kasih telah menyimak dari acara ini dari awal sampai akhir. Mohon maaf atas segala kekurangan dan kendala yang terjadi. Saya Via dan seluruh panitia undur diri. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Atur nuhun teh.
Ya, terima kasih. Thank you, Mr. Elhaj.
Terima kasih Teh, kok senyum-senyum.
Thank you very much.
Sekarang bahagia.
Pada pertanyaan nanti diskusinya bisa dilanjutkan lewat email. Mohon maaf sekali. Ini ada banyak partisipan yang mungkin memang spesifik ya, punya ketertarikan secara langsung di Vehicular Communication.
Siap.
Perlu deep conversation. Oke. Hatur nuhun.
Nuhun.
Assalamualaikum.
Waalaikumsalam.